A city in space needs its own gravity, and the solution is a simple, spinning ring. The engineering behind rotating space habitats is the master plan for humanity's permanent home among the stars. By the end, you will understand the precise calculations and trade-offs that could make these colossal orbital cities a reality. We will uncover why the very spin that creates a livable world also threatens to tear it apart, and how we might shield an entire civilization from the silent violence of deep space. What does it truly take to build a world from scratch? This force you feel on a merry-go-round is not a push from the walls, but a pull from your own inertia. Your body wants to travel in a straight line, but the spinning structure constantly redirects it inward, creating the sensation of being pressed outward. In the emptiness of space, we can harness this exact sensation. By designing a habitat as a rotating ring or cylinder, we turn the inside wall into the floor. Stand on that inner surface, and your own momentum, redirected by the curve of the structure, presses your feet down with a steady, familiar force. It is a brilliant illusion, a sleight of hand played with physics. Planetary gravity is a consequence of mass-warping spacetime, an attraction between objects. What we are engineering is a continuous acceleration, a constant change in direction that feels indistinguishable from weight to anyone living inside the ring. The strength of this artificial pull is not fixed. It is a product of two deliberate design choices. The first is how fast the habitat spins, its angular velocity. The second is its size, the radius from the central axis out to the living floor. These two numbers are locked in a delicate dance, and the relationship between them will dictate everything from the comfort of the residents to the very stability of the structure itself. This elegant equation holds a profound tension. To create a comfortable 1G of artificial gravity, you have two main levers to pull. You can build a habitat with a modest radius and spin it very, very fast. Or you can construct something truly enormous with a vast internal landscape and let it rotate at a gentle, leisurely pace. The math allows for both, but human biology firmly chooses a side. A small, rapidly spinning environment introduces a subtle but deeply unsettling force known as the Coriolis effect. If you were to toss a ball straight ahead in such a place, it would not travel in a straight line. From your perspective, it would curve mysteriously to one side, pour water from a bottle, and the stream would twist into a spiral before reaching the glass. Your inner ear, the delicate system that governs your balance, would constantly receive conflicting signals about which way is up and how your body is moving. For many, this would translate into persistent, debilitating motion sickness, turning a dream home into a nauseating prison. The engineering logic, therefore, becomes beautifully clear. To make a space habitat truly livable, we must minimize these physiological disruptions. That means we must prioritize a large radius, which in turn permits a slower, more graceful rotation. This single requirement for human comfort is what catapults our designs from the scale of a spacecraft to the scale of a city. It is why concepts like the Stanford Taurus envision a ring over 100 meters across, spinning once per minute. It is why more ambitious visions like the O'Neill cylinder propose structures miles in diameter, rotating just once every 2 minutes to generate a full Earth gravity. The choice of dimensions is never arbitrary. It is a calculated compromise, a direct negotiation between the limits of material strength and the fundamental needs of the human body. This pursuit of comfort, however, leads us directly to our next and perhaps greatest engineering challenge. The gentle spin that creates a comfortable home also generates a force of unimaginable power, pulling the entire structure relentlessly outward. Picture the habitat not as a solid block, but as a colossal, rotating ring. Every segment of that ring, every beam and panel, experiences a constant radial tug trying to stretch it apart. This is not like the compressive weight of a skyscraper where materials are squeezed together. This is pure tension, a force more akin to the stress on a gigantic spinning rope, where any weak point could lead to catastrophic failure. The entire habitat is in essence a structure flying apart, held together only by the incredible strength of its own bones. This defines the second, monumental design parameter, structural integrity under immense tensile forces. Primary engineering challenge shifts from creating gravity to simply surviving it. For the scales we have discussed, miles-wide cylinders or vast rotating rings, traditional construction materials like steel reach their limits. Their tensile strength, the maximum pulling stress they can endure before snapping, is simply insufficient. The logical path forward, then, points toward advanced materials science. Engineers look to composites, meticulously layered materials that combine for greater strength than their individual parts. They speculate about the potential of carbon nanotubes, with theoretical strengths hundreds of times greater than steel. They envision future alloys based on materials like graphene. The choice of material becomes the absolute foundation, the non-negotiable prerequisite that determines the maximum possible size and spin of the entire civilization. But material strength is only half the battle. A perfectly strong ring, if it is not perfectly balanced, becomes a death trap. Any significant asymmetry in mass, a slightly denser habitat sector, or an uneven distribution of cargo turns the entire structure into a wobbling top. This wobble, known as precession, would cause the axis of rotation to slowly trace a circle in space. Inside, this would not feel like a smooth spin, but a sickening, unpredictable lurch. The floors would tilt, the artificial gravity would shift direction, and the structural stresses would become chaotic and unbearable. Correcting this requires constant, precise, and energy-intensive thrust from attitude control systems, a burden no permanent settlement could afford. Therefore, the engineering logic dictates a form of elegant symmetry. The habitat's shape, whether a simple hoop like a Stanford Taurus or a pair of counter-rotating O'Neill cylinders, is not an aesthetic choice. It is a direct consequence of the force profile. These symmetrical shapes allow stress to be distributed evenly around the entire structure, minimizing weak points. They also make mass balancing a more achievable goal, as every segment can be designed as a mirror image of its opposite. The structure becomes a study in harmony, where every part works in concert to contain the tremendous forces within. Yet, building a perfectly balanced, immensely strong shell is merely creating an empty bottle. The true test of engineering is what we put inside it, a complete, self-regulating world that can sustain life indefinitely against the silent, absolute hostility of the vacuum outside. Building a world from scratch means confronting the most delicate engineering challenge of all, life itself. The spinning hull is merely a vessel, a breathtakingly strong but empty shell. To become a true home, it must contain a miniature Earth, a self-sustaining biosphere in perfect, perpetual balance. This is not simply a matter of packing enough supplies for the journey. It is about closing the loop entirely. Every breath taken, every drop of water consumed, every scrap of organic waste produced must be part of an endless, elegant cycle within the habitat's finite walls. The engineering logic here shifts from brute force mechanics to the intricate dance of ecology. We must replicate processes that on our planet are managed by vast, interconnected global systems, and we must do it with flawless reliability. The air cannot slowly become stale, the water cannot gradually become toxic, and the food supply cannot waver. A single persistent imbalance does not just mean discomfort, it means the slow, silent end of the entire enclosed civilization. This demands systems that are not only advanced but deeply integrated. Food production becomes the first pillar of life support. Vast, multi-tiered farms using hydroponic or aeroponic techniques would line dedicated agricultural sectors, their roots misted with nutrient-rich water, bathed in precisely tuned artificial sunlight. These are not just gardens, they are the settlement's lungs. As the plants grow, they perform the same miracle they do on Earth, absorbing carbon dioxide and releasing fresh oxygen, directly regulating the atmosphere. The water that nourishes them is never wasted. Every drop of moisture, from irrigation runoff to the humidity in the air exhaled by residents, is captured, funneled into advanced physico-chemical processes. Here, through a series of filters, distillation, and catalytic reactions, it is scrubbed of every impurity and returned to the system, crystal clear and ready to drink or feed the plants once more. Even human waste is not an endpoint but a resource. Bioreactors, teeming with carefully cultured microbes, would break down organic matter, reclaiming valuable water and nutrients to be fed back into the agricultural cycle. This creates a beautiful, closed loop where nothing is truly discarded, only transformed. Yet, for all its elegance, this artificial ecosystem is profoundly fragile. Redundancy is not a luxury, it is the core design principle. Multiple, independent food production modules, air scrubbers, and water purifiers must run in parallel. A single crop blight or a pump failure cannot be allowed to cascade into system-wide collapse. Engineers must design for graceful degradation, where the failure of one component is seamlessly compensated for by others, giving crews precious time to repair and restore. Furthermore, this entire biosphere must be engineered to exist comfortably within the habitat's unique conditions. The farms, the water systems, the air circulation, all must function perfectly under the constant, gentle pull of artificial gravity and within the subtle Coriolis forces of the rotating environment. The goal is to create a pocket of Earth so stable, so familiar, that a resident could forget they are living inside a machine, surrounded by the absolute void of space. But maintaining this illusion of a natural world, this perfect balance of air, water, and life, requires a constant, immense input of one thing: power. The lights for the farms, the pumps for the water, the computers monitoring every atmospheric variable, all demand a relentless and staggering supply of energy. This leads us to the final, foundational pillar of any space habitat, the question that underpins every other system: where does all this power come from, and how do we ensure it never, ever runs out? The entire civilization spins on a single, non-negotiable requirement: a constant and colossal flow of energy. This is the lifeblood of the habitat, powering the gentle rotation that creates gravity, the vast farms that produce food, the intricate machines that purify air and water, and the countless lights of a city that never sees a natural night. A permanent settlement cannot survive on shipments from Earth. It must become its own power plant, harvesting energy from the environment on a staggering scale. The engineering logic here is beautifully direct, pointing to the most abundant resource in the local solar system, the Sun itself. For a habitat in orbit around Earth or Mars, sunlight is a perpetual, torrential river of energy. Engineers envision vast fields of solar panels, perhaps arranged as immense static sails positioned just outside the rotating habitat, forever angled toward the Sun. These arrays would be measured not in acres but in square miles, capturing gigawatts of clean, silent power. But what happens when the habitat drifts into the shadow of a planet, or for settlements built farther out in the solar system where sunlight grows faint? For these scenarios, or for any civilization that demands absolute, uninterrupted power day and night, the calculations point toward a different source: nuclear fission. A compact, well-shielded reactor could provide the dense, reliable energy needed for centuries, a tiny artificial star at the heart of the colony. Yet generating the power is only the first step. You now face a fascinating puzzle. How do you deliver electricity to a city that is constantly spinning? Running physical cables from a stationary solar array to a rotating ring would result in them instantly twisting and snapping. The solution lies in clever engineering at the hub, the central axis of the habitat. One method could use rotating electrical couplings, sophisticated rings that maintain contact while allowing one side to spin freely against the other. Another, more elegant approach might employ targeted wireless power transfer, beaming energy as microwaves or lasers from a stationary transmitter to receivers on the rotating structure. This energy backbone makes everything else possible, but it introduces a final, invisible challenge. Every watt of energy used by the habitat, whether for light, computation, or even the friction of air circulation, eventually turns into waste heat. In the airless vacuum of space, there is no air to carry this heat away, no breeze to provide cooling. If left unchecked, the habitat would slowly cook itself, transforming into a sweltering, uninhabitable greenhouse. The engineering logic therefore demands a final, critical system, a way to balance the books on thermal energy, to radiate all that waste heat back into the cold depths of space. This becomes a silent, ongoing negotiation between the warmth of life inside and the absolute zero waiting outside the hull. The silent enemy of any sealed world is not cold but heat itself. Within the habitat, every action generates warmth, from the hum of a computer to the simple act of breathing. Sunlight pours in, machinery operates, and millions of lives go about their day, all adding to a constant, rising tide of thermal energy. On Earth, this excess heat is carried away by the atmosphere and oceans through convection, a process so seamless we never notice it. In the vacuum of space, that option vanishes. There is no air, no medium to carry the heat away. The only physical process left is radiation, the slow, steady emission of infrared light directly from a warm object into the cold void. This single, inescapable fact of physics dictates one of the habitat's most distinctive visual features, those vast, wing-like panels extending from its structure. These are not solar collectors but radiators, and they are the colony's lifeline, its only way to exhale its waste heat and maintain a stable, livable temperature. Their design is a masterclass in optimization. To radiate heat efficiently, they need an enormous surface area, often arranged into intricate fins or sprawling arrays. Their surfaces are engineered to be highly emissive, coated with special materials that excel at glowing in the infrared spectrum, effectively turning heat into invisible light that streams away into space. Yet, these colossal wings cannot be an afterthought. They must be carefully positioned to avoid casting shadows on solar panels or creating dangerous imbalances that could disrupt the habitat's smooth rotation. They are a permanent, active organ in the body of the settlement, working silently every second to prevent the interior from transforming into an unbearable oven. This battle for thermal equilibrium goes beyond the radiators themselves. Engineers must also manage thermal gradients, the differences in temperature across the massive structure. If one side, constantly facing the sun, grows significantly hotter than the shaded side, the habitat's hull will expand unevenly. This creates immense, silent stresses that could fatigue metal over time, leading to cracks or structural failure. The solution often involves clever circulation, using the habitat's internal atmosphere or liquid coolant loops as a kind of bloodstream, distributing heat more evenly before it is finally rejected by the radiators. It is a continuous, invisible balancing act, as critical as producing oxygen or growing food. Without this relentless process of thermal management, the delicate, closed-loop biosphere we worked so hard to create would simply stew in its own energy, making the entire engineering marvel uninhabitable. This leads us to a final, profound layer of the design, one that moves beyond mere survival. Once we have mastered the physics of gravity, structure, life support, and thermal control, we face the ultimate human question. How do we transform this perfectly tuned machine into a place that feels not just safe, but like home? How do we design for the human spirit within the spinning walls of a new world? But the cold void outside is not empty, it is filled with a silent, invisible storm. Beyond the challenge of managing our own warmth lies a far more insidious threat, a constant rain of high-energy particles known as cosmic radiation. On Earth, we are blissfully unaware of this bombardment. Our planet's thick atmosphere and powerful magnetic field act as a natural shield, deflecting and absorbing these particles long before they reach the surface. In space, our rotating habitat has no such protection. It is naked to the fury of solar flares, the relentless stream of the solar wind, and the penetrating galactic cosmic rays that travel from distant supernova. These are not mere nuisances, they are subatomic bullets that can slice through DNA, damaging cells and increasing long-term health risks, while also frying sensitive electronics. To build a permanent home, we must therefore engineer an invisible fortress, a radiation shield where nature provided none. The most straightforward logic in the engineer's toolkit is to use mass itself as a barrier. Just as a thick concrete wall stops more radiation than a sheet of paper, we can strategically use the very materials of the habitat to protect its inhabitants. The outer hull becomes the first line of defense, designed to be thick and dense, but the engineering goes deeper. The soil in the vast agricultural sectors, meters deep, becomes a brilliant dual-purpose layer, growing food while also absorbing harmful particles. Even the habitat's stored water, circulating in giant reservoirs or piping within the walls, can be routed to form liquid shields around the most sensitive areas like sleeping quarters and control centers. Every tank, every storeroom is positioned not just for convenience but as part of a calculated defensive geometry. This approach, called passive shielding, turns the necessities of life into a protective cocoon. Yet there is a trade-off known as the mass penalty. Every kilogram of shielding material is a kilogram that must be launched from Earth or mined and processed in space at tremendous energy cost. The engineering becomes a precise calculation, risk versus reward. How much radiation exposure is acceptable over a lifetime? How thick must the soil layer be to reduce it to safe levels? The answers determine the minimum mass required, shaping the entire habitat's design and the colossal scale of its construction. For visions of even greater safety, or for habitats traveling beyond the relative shelter of Earth's magnetosphere, engineers speculate about active shielding. This concept involves generating a powerful, localized magnetic field around the habitat, much like a miniature version of Earth's own, to deflect charged particles before they ever strike the hull. The idea is elegant, but the power demands are staggering, requiring energy systems far beyond anything we currently possess. For now, the silent, massive bulk of the habitat's own structure remains our most reliable guardian. This invisible layer of defense, woven into the walls, the soil, and the water, is what truly allows the artificial sky to feel safe. It is the final, critical engineering step that transforms a vulnerable machine into a sanctuary, a place where generations can look up at their sunlit landscape without fear of the silent storm just beyond the hull. With the fundamental systems of gravity, structure, biosphere, power, and shielding in place, we have blueprinted a machine that can survive. But a city is more than its infrastructure. It is the sum of the lives lived within it. At the very heart of this spinning world lies a place of profound stillness. The central axis of the habitat, the point around which the entire structure turns, is a realm of perfect weightlessness. Here, the artificial gravity engineered for the living rim simply fades away, creating a unique and strategically vital microgravity nexus. This hub is not an afterthought, but a deliberate feature born from pure engineering logic. Its primary function is as the habitat's front door to the universe. Docking a massive spacecraft to a spinning ring is a nightmare of precision, requiring the vessel to match the habitat's exact rotation before connecting. By placing the primary docking ports at the motionless hub, that complexity vanishes entirely. Ships can approach and anchor in standard zero gravity, a straightforward procedure we already understand. From this silent, weightless atrium, the transition into the habitat's living world begins. Passengers and cargo board elevators or trams that travel down the long spokes connecting the hub to the outer rim. As they descend, the centrifugal force gradually takes hold. The feeling of weight returns, growing stronger with every meter, until they step out onto the landscape of the inner surface, under the full pull of artificial gravity. This journey from weightlessness to weight is a daily experience, a physical passage between two completely different environments contained within the same structure. Beyond its role as a port, the hub's microgravity makes it invaluable for specialized work. It can house sensitive laboratories where researchers can conduct experiments impossible on Earth or on the rim, studying fluid dynamics, material formation, or biological processes in pure freefall. It could host crystal-clear observatories, their telescopes unshaken by atmospheric distortion, or even the subtle vibrations of the rotating habitat. The central command center for the entire colony might reside here, offering a stable, panoramic view of both the interior world and the external cosmos. This creates a dynamic internal geography. The bustling, Earth-like rim with its towns, farms, and open skies stands in contrast to the silent, technical heart at the center, connected by the steady transit along the spokes. This multifunctional hub is the critical interface between the living world inside and the void outside, a transition zone that must be meticulously controlled. Airlocks here are not simple doors, they are complex chambers managing the differential between the vacuum of space and the habitat's thick atmosphere, all while ensuring that no twist or torque is ever transferred to the spinning structure below. It is a place of constant, silent protocol where engineering precision ensures the safety of everyone within. This elegant division of environments, from the weightless hub to the gravitated rim, showcases a deeper principle. It proves that within our engineered world, we are not limited to a single reality. We can create the conditions we need exactly where we need them. But this mastery over our immediate environment leads to a larger, more daunting question. Once we have built the first perfect habitat, a closed, self-sustaining ark, what comes next? How does a single settlement grow into a civilization, and what new scales of engineering would that future demand? These spokes are far more than simple support beams. They are the dynamic arteries of the entire habitat. Picture a long, slender tube stretching from the motionless hub down to the bustling, spinning rim below. Inside this tube, an elevator car begins its descent. At the top, in microgravity, it feels weightless, but as it moves downward along the curved spoke, it must gradually match the increasing rotational speed of the rim. To a passenger, this would feel like a gentle return of weight, a smooth transition from floating to standing as the centrifugal force takes hold. The engineering challenge here is one of seamless integration, ensuring this transition happens without a single jolt, lurch, or moment of vertigo. A conventional cable elevator with its pulleys and gears would struggle with the complex forces and could transfer unwanted vibrations into the delicate structure. The logical solution points toward magnetic levitation. A maglev system within the spoke could propel the elevator car silently, with no physical contact, allowing for perfectly controlled acceleration and deceleration. It would be a journey of profound quiet, where the only noticeable change is the gradual feeling of your own body settling into itself, a reverse birth into a world of artificial gravity. Once you arrive on the rim, you step out into a landscape that defies earthly intuition. The ground curves upward in both directions, eventually meeting high overhead. In this world, up is not toward the sky, but toward the distant central axis, and down is always outward, toward the hull beneath your feet. This reoriented reality shapes every aspect of transportation and urban planning within the habitat. You could not simply build a straight road that goes on forever. It would eventually curve upward into a wall. Instead, transit systems must be designed for a closed, circular world. A tram line would run along the circumference of the rim, a never-ending loop that could carry you around the entire interior. Personal vehicles would be possible, but driving would require constant, subtle steering to follow the curve of the landscape, making long, straight highways an impossibility. The flow of people and materials becomes a three-dimensional puzzle. Major towns might be spaced along the rim, connected by fast circumferential transit. But to travel inland toward the central axis, you would take a local spoke elevator up to a higher level, where the rotational speed is slower and the effective gravity is lighter, perhaps to reach a specialized research platform or a quieter residential district. This vertical dimension adds a layer of complexity utterly foreign to earthly cities. The very layout of a habitat city, the placement of its parks, its industrial sectors, and its residential blocks, is dictated by these novel physics. Planners must consider not just distance, but gravity, gradient, and sight lines in a world where you can see the back of your own head, far in the distance across the curved interior. It is urban design reimagined from first principles, creating a society that lives comfortably inside the curve of its own engineered horizon. Standing on the inner surface of this world, you are surrounded by the landscape itself. The ground does not stretch to a distant, flat horizon as on Earth, but curves steadily upward in front of you, sweeping over your head to meet itself on the far side of the enormous cylinder or ring. You are literally standing inside the world with the entire habitat wrapped around you. This is the most profound psychological challenge of the design, a built environment where every instinct about perspective and space is gently but persistently challenged. The engineering logic, therefore, must extend beyond physics and into the human mind. To prevent a constant, low-grade sense of disorientation, the interior must be carefully crafted to create a perceived flat horizon, a comforting line that separates land from sky even when the geometry says otherwise. This is achieved through a masterful blend of terrain manipulation, architectural scale, and visual trickery. Designers would use rolling hills, strategically placed clusters of taller buildings, or even carefully positioned stands of trees to block the direct view of the land curving upward. The goal is to segment the vast interior into manageable vistas, where your immediate surroundings feel reassuringly normal, and the more dramatic curvature is experienced as a distant, almost mountainous backdrop rather than an overhead ceiling. It is a grand illusion, an architectural sleight of hand that makes an alien geometry feel like home. Central to this illusion is the sky, or rather, what takes its place. Since there is no atmosphere extending to infinity, the sky is another engineered feature. One elegant concept involves a long, brilliant strip of light running the length of the cylinder's central axis, like a captured sliver of the sun. This axial mirror or light tube would be segmented, with portions that could be dimmed or shuttered to simulate the passing of clouds and the gradual dimming of dusk. It would create a soft, diffuse light that casts shadows and gives depth to the interior landscape, orchestrating a convincing 24-hour cycle of day and night. Below this artificial sky, the most ambitious element takes root, the biosphere floor. This is not a thin layer of astroturf, but a deep, living foundation. Engineers would deploy a robust geomembrane, a high-tech liner, to contain the entire ecosystem. Upon this, they would build up meters of engineered soil, rich with nutrients and tailored for the plants selected to thrive there. Rivers could be channeled from central reservoirs, flowing along curated paths to lakes, their currents subtly managed by the habitat's rotation. Trees would grow to a certain height, their canopies helping to further obscure the curving vista above. The air itself, a carefully mixed balance of nitrogen and oxygen, is held in by the immense hull, pressurized and continuously scrubbed by the life support systems. This is the grandest interior design project in history, transforming the inside of a machine into a place of meadows, streams, and community. It is about using every tool of landscape architecture, urban planning, and environmental psychology to forge not just shelter, but a profound and enduring sense of place. The ultimate success of the habitat is measured not in megawatts or structural tolerances, but in the moment a resident looks out their window and feels, simply, that they are home. Yet, this carefully crafted stability exists within a system of immense forces, and the greatest designs must account for a fundamental truth: nothing in space is ever truly static. A world of such delicate balance cannot afford to drift, unlike a planet whose immense mass anchors it on a predictable celestial path. A space habitat is a featherweight in the cosmic winds. Its negligible mass makes it susceptible to countless subtle nudges: the gravitational tugs from the moon or a passing asteroid, the gentle but constant push of sunlight itself, known as solar radiation pressure. Even in what we call the vacuum of low Earth orbit, a few stray molecules of atmosphere create a whisper of drag, slowly but surely stealing energy and altitude. This reality forces a fundamental shift in perspective. The habitat is not a fixed world, but a vessel that must constantly navigate. It cannot be built and left alone. It requires perpetual, active station keeping. The engineering logic here demands propulsion, but not for grand voyages. Instead, it calls for systems of exquisite patience and precision, like ion thrusters. These devices work by electrically charging atoms of a gas like xenon and accelerating them to tremendous speeds to generate thrust. The force they produce is minuscule, often compared to the weight of a single sheet of paper resting on your hand. But in the frictionless realm of space, this whisper of force, applied continuously over months or years, is more than enough to make the minute adjustments needed to hold the habitat's position. This silent, ongoing ballet of correction is not optional. It is the bedrock of all other systems. Stable solar power collection requires the habitat's vast arrays to remain pointed squarely at the sun. Clear communication with Earth depends on maintaining a reliable line of sight. Most critically, it allows for proactive debris avoidance, gently maneuvering the entire city out of the path of a fast-moving scrap of metal that could puncture the hull and end everything. The choice of where to park this civilization is therefore one of the first and most consequential calculations. An orbit close to Earth, in low Earth orbit, offers relative accessibility for resupply and crew rotation, but it comes with higher debris risk and passes through the edges of Earth's protective magnetic field, creating complex radiation zones. Alternatively, engineers might choose a location of gravitational harmony, like a Lagrange point. These are places in space where the gravitational pulls of two large bodies, like the Earth and the Sun, create a stable point where a smaller object can essentially park with minimal effort. A habitat at a Lagrange point would experience far less orbital perturbation, requiring less station-keeping fuel and enjoying a constant, unimpeded view of the sun for power. Yet, this profound stability comes at the cost of profound isolation, making resupply missions far more difficult and lengthy. Each orbital choice ripples through every other system, affecting the design of the shields, the capacity of the life support reserves, and the very social fabric of a community that may be only a few days or many months away from help. The habitat does not orbit passively. It is perpetually engaged in a dialogue with the universe, using the faintest of touches to maintain its place in the void. The final, most daunting layer of engineering is not the design but the doing. We have a blueprint for a world, but how do you build a city the size of Manhattan when the nearest hardware store is 250,000 miles away? The sheer physics of rocketry make the traditional approach, launching every beam and panel from Earth's surface, an economic and practical impossibility. The fuel costs alone would be staggering, and the launch rate required would dwarf all of human spaceflight history combined. The engineering logic, therefore, makes a radical pivot. It points away from our planet and into the resource-rich environment of space itself. The only viable path forward is to become builders of the void, using materials we find already floating in the cosmic neighborhood. This concept is known as In-Situ resource utilization, and it transforms the entire project from a shipment into a settlement. The most promising construction yards are not on Earth, but on the Moon and in the asteroid belt. The Moon offers vast deposits of metals like iron and aluminum locked within its regolith, the dusty soil that covers its surface. Nearby asteroids are even richer, often composed of nickel iron, precious metals, and critically, water ice. This water is not just for life support, it is a foundational resource. Through a process called electrolysis, it can be split into hydrogen and oxygen, the most powerful chemical rocket propellants we know. This means the very act of mining fuel could eventually power the mining operations themselves, creating a self-sustaining industrial chain far from Earth. Imagine automated harvesters landing on a metallic asteroid, not to bring it back whole, but to process it on site. They would use focused solar furnaces, giant mirrors concentrating sunlight into a beam of pure heat to melt and separate raw ore. In the airless silence, other machines would form this material into standardized beams, hull plates, and wire, the basic bones of the habitat. This off-world factory, humming with robotic activity, would be the first true industrial base beyond our world. But then you face the assembly. You cannot simply weld in a vacuum the way you do on Earth. Traditional welding relies on atmospheric gases to protect the molten metal. In space, you must develop new techniques, perhaps using electron beams or lasers in sealed chambers to fuse materials together. The construction robots that perform this work would need to be incredibly versatile, capable of precise manipulation in microgravity while anchored to a growing structure. They might be teleoperated by human pilots safely back on Earth, working with a time delay, or guided by sophisticated artificial intelligence that can interpret blueprints and adapt to unforeseen challenges in real time. The build itself would likely be incremental, a proof of concept growing into a civilization. Engineers might start with a small, rotating test ring, just a few dozen meters across, to validate the principles of artificial gravity and structural integrity. Once those are proven, construction would scale up. The first permanent habitat might begin as a single, modest torus. Over decades, new rings could be added, connecting to a central hub like petals on a flower, eventually forming a vast, rotating flower of life in the dark. The construction site itself, this zone of raw creation, would be a temporary city of its own. It would require pressurized hangars for sensitive work, power stations fed by immense solar arrays, and safe havens for any construction crews that might venture out from Earth to oversee the work. It poses a profound, almost philosophical question about our future. Does a civilization truly begin when the first family moves into their new home on the rim? Or does it begin with the first robotic claw that scoops metallic ore from an asteroid? The act of building these habitats is not just a technical challenge. It is the very process of learning to live independent of our cradle, forging our future from the raw materials of the cosmos. The staggering scale of such a project demands more than just a technical blueprint. It requires a reason to exist, a compelling economic engine powerful enough to justify the centuries of effort and trillions in investment. Engineering logic must find its partner in financial logic. For a civilization to truly take root in space, the habitat cannot be a mere sanctuary. It must become a productive hub, a place where value is created in ways impossible on Earth. The most powerful driver could be space-based manufacturing. The unique environment offers two priceless commodities: pure, hard vacuum and persistent microgravity. In orbital factories, we could grow flawless crystals for next-generation semiconductors, blend metals into exotic new alloys that cannot form under Earth's gravity, or develop revolutionary pharmaceuticals with purer, more complex molecular structures. These are not just products, they are technological leaps that could fuel entire new industries back on Earth, creating a high-value export stream from orbit. Another profound economic possibility lies in turning the surrounding void into a resource frontier. Robotic prospectors could harvest water ice from asteroids or the moon, splitting it into hydrogen and oxygen to create the very rocket fuel that powers further expansion. They could extract platinum group metals, rare on Earth but abundant in certain asteroids, for use in advanced electronics and clean energy technologies. The habitat, positioned as a central processing and support station, becomes the heart of this new industrial chain. It provides a stable, human-tended base for remote operations, a place to refine raw materials, and a home for the engineers and technicians who keep the robotic fleets running. This creates a powerful feedback loop. The profits from space-based industry fund the habitat's expansion, and the growing habitat enables more ambitious industrial projects. The initial step would likely be a small, rotating industrial station, focused on a single high-value product like specialized fiber optics or pharmaceutical research. Its success would attract more investment, allowing it to grow, add new modules, and gradually incorporate more life support and residential sectors. Over time, this purely functional outpost evolves organically into a true settlement with families, schools, and cultural centers. The habitat transforms from a cost center into both the factory and the marketplace, a closed economic ecosystem in the sky. Yet, this grand vision of a self-sustaining orbital economy hinges on a single, fragile variable: the people who must live and work there. The entire financial model assumes a permanent, productive workforce. This forces us to confront the ultimate, non-negotiable constraint, not of engineering or economics, but of human biology itself. Can the human body truly adapt to a life lived entirely inside a spinning can, under artificial light, shielded from a natural sky for generations? The success of the entire endeavor rests on the answer to a deeply personal question, one that moves from boardrooms and blueprints into the very cells of our being. The final blueprint for a space habitat is not complete until we place a person inside it. Engineering must serve biology, for the most complex and delicate system we will ever install in this new world is the human body itself. Evolved over millions of years for Earth's precise gravity, atmosphere, and rhythms, our physiology presents the ultimate design constraint. We have calculated the large radius to minimize the disorienting Coriolis effect, but subtle differences may persist. Imagine a child growing up in this environment, their inner ear calibrated from birth to a world that spins once every 2 minutes. Would a simple game of catch feel perfectly normal, or would their brain process motion in a slightly different way? These are not hypotheticals, they are essential questions for long-term habitation. Medical research in space has already shown us that in microgravity, the body undergoes profound changes. Fluid shifts toward the head, muscle atrophy, and bone loss as the skeleton no longer fights gravity. Our artificial gravity is designed to prevent that, but we must study how the body regulates blood pressure along the habitat's vertical axis, from the higher gravity at the rim to the lower gravity near the hub. Would cardiovascular systems adapt seamlessly, or would novel health patterns emerge over decades? The habitat's medical facilities cannot be mere clinics. They must be advanced research hospitals capable of diagnosing and treating conditions we have not yet named, born from an environment we ourselves created. This biological adaptation extends beyond the physical. Psychological well-being in a closed, artificial world demands its own careful engineering. There is no natural weather, no unbidden breeze, no open horizon that stretches to infinity. The sky is a crafted light source, the ground curves gently overhead, and every tree is planted by human hands. To prevent a deep sense of confinement or alienation, the design must actively nurture the human spirit. Communal spaces become vital organs of the society, grand atriums with real trees and flowing water that provide a sensory connection to life. Windows to the external universe, strategically placed in residential areas or transit hubs, are not just viewports, they are psychological lifelines, reminding residents of their place in the cosmos and offering a profound sense of context. Recreational areas must offer more than distraction. They must provide challenge and variety, from sports fields under the axial light to microgravity gymnasiums at the hub for flight and play. The soundscape itself might be designed with recordings of earthly birdsong or rustling leaves woven into public gardens to comfort the subconscious. The ultimate test of all our engineering is not whether the hull holds or the air remains breathable. It is whether people can thrive here, not just for a mission, but for generations. This consideration gently nudges us toward a horizon of thought far beyond blueprints and construction schedules. If humanity truly makes its home in these spinning arcs, raising children who know no other world, what subtle whispers might evolution itself begin to impart over centuries? The principles of rotating habitats find their ultimate expression in the visionary work of physicist Gerard K. O'Neill. His design, known as the O'Neill cylinder, moves beyond theory into a breathtakingly detailed vision for a permanent human home. It is a case study in grand scale and elegant compromise. The core concept features not one, but two enormous cylinders, each several miles in length and diameter, rotating side by side. They spin in opposite directions, connected through a sophisticated central bearing system. This counter-rotation is a masterstroke of engineering logic. It cancels out the powerful gyroscopic forces that would otherwise make the entire structure stubbornly resist any change in orientation. With this design, the habitat can be gently turned, its vast windows angled to best capture sunlight without fighting the physics of its own spin. Inside, the scale is deliberately planetary. Each cylinder offers a living landscape so vast that the curvature of the land becomes a distant, gentle rise, like living in a broad valley. The interior is divided into alternating strips, long bands of land for towns, farms, and forests, running alongside equally long, transparent windows that look out onto space. Here, the challenge of an artificial sky is solved with sublime elegance. External, stationary mirrors, vast and computer-controlled, capture raw sunlight and reflect it inward through the windows. By adjusting these mirrors, the system can simulate the soft arc of a sunrise, the brightness of noon, and the gradual dimming of dusk, painting a convincing day-night cycle across the entire interior. Rivers could flow from lakes at one end of the cylinder, and clouds might even form in the pressurized air, drifting beneath the mirrored sunlight. This is not a cramped station. It is a declaration that space itself is our new frontier for living, not just for working. The O'Neill cylinder embodies every critical trade-off we have discussed. Its immense radius, measured in miles, allows for a slow, comfortable rotation of about 1 revolution every 2 minutes to produce full Earth gravity, minimizing the disorienting Coriolis effect. Its counter-rotating design solves the stability problem of precession. Its mirrored light system addresses the colossal energy and thermal management needs by using pure, reflected sunlight as the primary illumination. It is a holistic architecture where every system supports another. The land strips provide radiation shielding mass. The agricultural sectors are integral to the life support loop, and the sheer volume of air and water creates a robust thermal buffer. This design philosophy represents a fundamental shift in thinking, from viewing space as a hostile environment to be endured in tiny capsules, to seeing it as a place where we can engineer entire new biospheres crafted for human flourishing. As a concrete template, it sets a high bar for ambition. It asks us what level of comfort, stability, and beauty we are willing to engineer into existence, and in doing so, it gives us a tangible goal against which to measure our technological progress for the next century. While the O'Neill cylinder offers a grand vision of planetary-scale living, its very ambition pushes it into the distant future. A more immediate blueprint exists, one that scales the dream down to a size we might realistically build within a century. The Stanford Taurus is a design of elegant compromise, a rotating wheel roughly 1 mile in diameter where the entire living surface is a single, habitable ring along its inner rim. Picture a colossal bicycle tire spinning silently in the void, with towns and fields curving gently upward along its interior. This is not a substitute for the cylinder's vastness, but a deliberate and pragmatic alternative. Its smaller scale presents a different set of calculations and trade-offs, embodying the engineering logic of incrementalism. Where the O'Neill design aims for a final, permanent home, the Taurus is conceived as a critical stepping stone, a prototype city where we can learn to live in artificial gravity before attempting to build a world. The primary compromise is written in its spin rate. To generate a full Earth gravity within its 1 mile radius, the Taurus must complete a full rotation approximately once every minute. This is significantly faster than the leisurely 2-minute spin of a miles-wide cylinder. That faster rotation brings the Coriolis effect, that subtle force that deflects moving objects into sharper focus. In a Taurus, a casually thrown baseball might curve noticeably over a long distance, and water draining from a sink would swirl with a more pronounced twist. The question for designers is whether human physiology can adapt to these persistent, low-level cues, or if they would forever serve as a reminder of the habitat's artificial nature. To mitigate this, the interior layout would be carefully zoned. High-activity areas like sports fields might be placed at the very rim where gravity is strongest and most consistent, while quieter residential sectors could be situated on terraced levels slightly inward, where the rotational speed is marginally slower and the Coriolis forces are reduced. The structure itself is a masterpiece of focused engineering. A large, stationary mirror positioned alongside the rotating ring captures sunlight and beams it through a series of windows running the length of the habitat, creating a convincing cycle of day and night within the ring. The central hub, motionless in space, serves as the docking port and a microgravity factory, connected to the living ring by the long spokes that carry elevators and utilities. This design drastically reduces the sheer volume of material required compared to an O'Neill cylinder, making the sourcing of metals and composites from the moon or asteroids a more manageable first goal for off-world industry. The Stanford Taurus does not promise the open horizons of its larger cousin. Its sky is a strip of windows looking out onto space, and the land curves upward more noticeably, creating an intimate, valley-like environment. Yet, in this intimacy lies its purpose. It represents a feasible test bed for every critical system, from closed-loop ecology and radiation shielding to the social dynamics of a community living in a completely engineered space. Success here would provide the confidence, the technological pedigree, and the economic framework to justify the next grander leap. It proves that the principles of rotating habitats are scalable, that we can start with a village in the sky, and once we have mastered its rhythms, expand our vision to encompass entire new lands under an artificial sun. But the engineering of gravity is not an all-or-nothing proposition. the rotating habitat offers a unique power, the ability to fine-tune the very force that holds us down. We are not limited to replicating Earth's 1G. We can design a spectrum of gravity within the same structure. This is the principle of the gravity gradient, and it transforms the habitat from a simple imitation of home into a versatile, multi-zone laboratory for living. Imagine a series of concentric rings within the larger cylinder, each spinning at a slightly different speed. The outermost ring, with the largest radius and fastest tangential velocity, might provide the familiar 1G for everyday life. But move inward to a smaller, slower spinning ring, and you step into a world of lunar gravity, perhaps 0.3G. Here, movement would feel buoyant and effortless, a permanent low-gravity playground. This is not just a novelty, it is a tool. Such zones could be dedicated to specialized activities, from high-jump athletic training that defies earthly limits to delicate manufacturing processes where materials behave differently in partial weightlessness. More profoundly, these graduated rings become long-term research platforms for human health. We could study how the human body adapts to Martian gravity over decades, or whether a gentler 0.5G might be sufficient to maintain bone density and cardiovascular health for permanent residents, reducing the structural demands on the entire settlement. The interfaces between these zones, however, require their own elegant engineering. Moving from a 1G residential ring to a 0.3G research ring would likely involve a transit system along a radial spoke, where the change in simulated gravity is experienced as a gradual lightening, not a sudden shift. The mechanical coupling between rings spinning at different speeds is a challenge of bearings and power transfer, but it is a solvable one. This granular control over our environment represents a fundamental shift in thinking. We are no longer trying to escape gravity or merely copy it. We are learning to dial it to our specific needs, crafting the physical conditions most suitable for the task at hand, whether that task is raising a family, forging a new alloy, or unlocking the secrets of long-term human adaptation to worlds we have yet to build. The silent symphony of a functioning habitat is conducted by an intelligence woven into its very walls, managing millions of interdependent systems. From the precise mix of breathable air to the subtle adjustments of 1,000 radiator panels is a task of such immense complexity that it surpasses unaided human oversight. The engineering logic, therefore, does not just welcome automation and artificial intelligence, it demands them as fundamental components. This digital nervous system would be built from a vast, living network of sensors embedded everywhere, monitoring pressure in water lines, trace gases in the atmosphere, structural stress points on the hull, and even the spectral quality of light in the agricultural bands. This constant stream of data flows into a central artificial intelligence, a system whose primary purpose is not to command, but to perceive, predict, and preserve. It would operate as the ultimate guardian of equilibrium, running millions of simulations in real time to anticipate problems before they arise. It could detect a slight, anomalous vibration in a spoke elevator motor, schedule a maintenance drone for inspection, and reroutine passenger traffic, all before a human operator ever noticed a warning light. It would manage the intricate dance of resource allocation, deciding in a moment whether to route extra power to the water recyclers during a peak usage period or to temporarily dim the axial mirrors to conserve energy, all while keeping every variable within the narrow green bands that mean life. This AI becomes the habitat's silent, ceaseless heartbeat, handling the staggering burden of routine operations so that the human residents are freed from the control panels. They are not relegated to mere passengers, but elevated to their most essential roles as explorers, scientists, artists, and community builders, engaging with the world their machines maintain. The reliability of this system is as non-negotiable as the tensile strength of the hull's materials. Its programming must be an exercise in profound ethical engineering, built with layers of fail-safes and a core directive aligned unambiguously with human well-being and the preservation of the biosphere. It represents the ultimate fusion of disciplines, where digital logic and physical engineering merge to create not just a structure, but a truly autonomous living world. Even the smallest grain of sand becomes a bullet in the silent void. Orbital debris, ranging from spent rocket stages to flecks of paint, and micrometeoroids, natural particles of dust and rock, travel at velocities measured in kilometers per second. At those speeds, a marble-sized object carries the kinetic energy of a falling anvil, capable of blasting a catastrophic hole through conventional spacecraft hulls. For a habitat containing an entire atmosphere and a civilization, this is not a remote risk, but a constant statistical certainty. The engineering response cannot be a single, thick wall, which would be prohibitively heavy, but rather a clever, multi-layered defense system designed to dissipate that incredible energy before it reaches the living space. The first line of defense is often a Whipple shield named for its inventor. Think of it not as armor, but as a sacrificial bumper. It is a relatively thin outer skin, spaced several centimeters away from the habitat's main pressure hull. When a high-speed particle strikes this outer bumper, it does not punch a clean hole. Instead, it and a portion of the bumper itself vaporize instantly into a cloud of superheated gas and debris. By the time this expanding cloud reaches the primary hull behind the gap, its energy has spread over a much wider area, reducing its punch to something the main structure can easily withstand. This elegant principle turns a deadly projectile into a manageable splash. Behind this bumper shield lies the habitat's primary radiation shielding, the layers of soil, water, and hull material. This mass now serves a dual purpose, further absorbing any residual energy from an impact and stopping secondary radiation. For the most critical areas, like command centers or primary life support nodes, engineers might design redundant hull layers or incorporate self-sealing materials that can temporarily plug a minor puncture. Yet this passive shielding is only half the strategy for larger objects, those bigger than a softball, that could overwhelm even the best Whipple shield. Here, the habitat must become nimble. Advanced tracking networks on Earth and in orbit would constantly monitor the paths of known debris, calculating potential collision courses. Upon receiving a warning, the habitat station-keeping thrusters, those same gentle ion engines used for orbital maintenance, would fire a precise maneuver, nudging the entire city a few hundred meters to one side, allowing the threat to pass harmlessly by. This entire defensive architecture, from the vaporized particle to the orchestrated dodge, is a calculated addition of mass and complexity. It is the necessary price of permanence, a silent guardian ensuring the long-term integrity of the pressurized world against the inevitable peppering of space. Every layer is a reminder that the serene landscape under the artificial sky exists within a shooting gallery, and that survival is an active, engineered condition. This constant vigilance against external threats forces us to look inward, to consider the social fabric that must hold this isolated community together through challenges we can scarcely foresee. The most resilient alloy in the habitat is not in its hull but in the bonds between its people. We have engineered a world of perfect physics, but a civilization is built from choices, not calculations. Within these spinning walls, every decision about water, food, and living space is magnified by the simple, inescapable truth: there is no outside to escape to. Traditional models of governance, built for open societies with frontiers and external trade, may buckle under this pressure. The habitat demands a new social calculus, one that balances individual liberty with collective survival in an environment of absolute scarcity and absolute interdependence. This is the ultimate soft engineering challenge, designing the invisible structures that will allow a community to thrive for generations. The physical layout becomes the first draft of this social contract. Wide, open promenades connecting residential blocks to communal farms are not just transit corridors, they are designed encounters, spaces that encourage conversation and shared purpose. Smaller, terraced neighborhoods with private gardens offer necessary retreats, acknowledging the human need for solitude and personal domain. The placement of a town hall, a school, or a market is a deliberate signal about what the community values, shaping daily life as surely as the rotation creates gravity. Engineers and architects must now work hand in hand with sociologists and psychologists, asking not just if a structure can hold air, but if it will hold a society together during a crisis. Resource allocation moves from an engineering spreadsheet to a central pillar of civic life. In a world where every calorie of food and every liter of water is meticulously tracked by the central life support AI, the concept of waste takes on a moral dimension. Systems would likely be designed for radical transparency, allowing every resident to see the status of the shared biosphere, fostering a sense of collective stewardship. The principle of equity becomes a practical necessity, as severe inequality could lead to social fractures that jeopardize the operation of critical systems for everyone. Conflict resolution mechanisms must be robust and perceived as fair, because a grievance left to fester could escalate in an environment where there are no separate nations to move to. The legal framework itself must evolve, grappling with novel questions of jurisdiction, privacy under constant system monitoring, and the rights of individuals within a community that literally cannot afford dissent that threatens its physical infrastructure. The habitat's success, therefore, is measured by two interdependent metrics: the stability of its atmospheric pressure and the stability of its social fabric. One ensures the body lives, the other ensures the spirit endures. This profound integration of the social and the technical hints at a future where our greatest engineering achievement might not be the mastery of spin and radiation, but the conscious design of a society built from the ground up for harmony and resilience. The world outside your window is the final piece of the puzzle. We have engineered gravity, structure, and sustenance, but the view upward presents a profound psychological frontier. The ceiling of a rotating habitat is not a sky in the earthly sense. It is a manufactured surface, perhaps a mirrored strip reflecting the opposite curve of land, or a vast screen projecting a comforting image of Earth's clouds. For a species whose moods, art, and sense of time have been shaped by the open heavens, this manufactured ceiling risks inducing a deep unease, a condition sometimes called sky shock or landscape deprivation. It is the subtle, persistent grief for a horizon that does not exist, for weather that is not random, for a sense of boundless space that has been gently walled away. This is not a trivial concern. It is a critical engineering parameter for long-term well-being, a problem of perception and mental health that must be solved with the same rigor as radiation shielding. The logic of the design must therefore extend to the human soul, asking how we can maintain a connection to the cosmos while living safely within a can. One elegant solution lies in transparency, but of a very specific kind. Engineers might design vast viewports not as weak points but as armored observatories. Using layers of fused silica or advanced transparent ceramics, incredibly strong materials that can withstand micrometeoroid impacts, these windows would offer actual, unfiltered views of the starry blackness, the swirling marble of Earth, or the rusty disk of Mars. They become psychological airlocks, places where residents can go to be dwarfed by the universe, to remember their place in a grander story, and to counter the potential claustrophobia of an entirely human-made world. Alternatively, the interior ceiling could become the most sophisticated canvas in history. Advanced display technology, using micro-LEDs or projection systems, could simulate not a static picture, but a dynamic, algorithmically generated sky. It could display a real-time feed from external cameras, creating the illusion of living under a glass dome. It could even artistically interpret data, turning the solar wind into gentle aurora-like waves of color that dance across the overhead landscape. The goal is not to deceive, but to comfort and inspire, to provide the visual and emotional cues of a dynamic, infinite environment. This addresses a core human need for awe, for a vista that stretches beyond our immediate concerns. A habitat that solves for physics but neglects this need for cosmic connection risks building a perfectly functional prison. The most successful designs will be those where a resident, after a long day, can look up and feel not confinement, but wonder, ensuring the spinning world feels less like a survival pod and more like a balcony looking out onto the universe itself. The gentle spin that defines this world is not a permanent state but a carefully managed condition. Bringing a megastructure from a standstill to its full rotational speed is an event of staggering power and precision. You cannot simply fire a giant thruster on one side that would twist the entire habitat like a top, creating immense, uneven stresses. Instead, engineers would choreograph a symphony of smaller thrusters positioned around the rim, each firing in perfect sequence to apply torque evenly. The process would be agonizingly slow, a gradual increase over weeks or even months, allowing the immense structure to gently settle into its new dynamic equilibrium. Every beam and joint would be monitored by thousands of sensors, watching for any sign of unexpected flex or vibration. The energy required is colossal, drawn from the habitat's solar arrays or perhaps a dedicated startup reactor, all to impart the angular momentum that will become the settlement's most vital property. This spin-up is the true birth of the artificial gravity, the moment the machine awakens to its purpose. But what happens when the spin must stop? Planned maintenance on the central hub, a major structural repair, or a dire emergency like a critical hull breach could necessitate a controlled spin down. Halting the rotation presents a different, more treacherous set of challenges. Inside, everything that is not bolted down, from the water in the reservoirs to the very atmosphere, has been moving with the spin. A sudden stop would cause this fluid mass to slosh violently, creating chaotic pressures that could rupture tanks and pipes. The structure itself has a natural resonant frequency, and a poorly managed deceleration could excite these vibrations, amplifying stress at the worst possible moments. Therefore, spin down must be a mirror of the startup, a gradual, meticulously plotted reversal. The rotational energy cannot simply be wasted as heat, it is too valuable. Engineers would likely capture it using massive flywheels or fluid-filled gyroscopes, storing that angular momentum in a controlled way so it can be used to spin the habitat back up once the work is complete. These systems transform the habitat from a static concept into a dynamic, living machine. They grant its caretakers the ultimate control over the force that defines daily life, allowing them to cradle an entire civilization safely through the profound transitions between motion and rest. The grand visions of spinning cities are not idle dreams, they are engineering roadmaps being actively validated. The journey from concept to reality is paved with 1,000 small, deliberate experiments. Before we can build a world, we must first prove we can sustain a single life for a year, then a decade, then a generation, using nothing but what we bring and recycle. The International Space Station serves as our most critical prototype, a laboratory for the closed-loop systems that will one day breathe life into a habitat. Every drop of water reclaimed by its advanced purification system, every kilogram of oxygen generated by its electrolysis units, is a quiet triumph. These are not just technical achievements, they are the first successful notes in the symphony of a self-sustaining biosphere. A water recycler that operates flawlessly for years in microgravity is more than a machine. It is a promise that the intricate cycles of a larger world are possible. Alongside life support, the very materials of our future are being forged and tested. research into new space-rated composites, substances that can withstand the brutal temperature swings and radiation of the void while remaining strong and light, is accelerating in labs on Earth. Companies are pioneering techniques for in-space manufacturing, experimenting with three-dimensional printing using metals or regolith simulants in vacuum chambers. Each new alloy, each successful print of a structural beam in simulated conditions, is a brick laid in the foundation of our off-world construction industry. We are learning to build with the materials we will find, turning the problem of supply into an opportunity for innovation. Perhaps the most intimate frontier of research is the human body itself. How does prolonged exposure to artificial gravity, or the lack of it, reshape our physiology? NASA and other agencies use short-radius centrifuges, compact devices that spin human test subjects, to study the effects of different gravity levels on bone density, muscle mass, and cardiovascular health. These experiments are crucial for determining the minimum spin rate and radius needed for long-term health, directly informing the dimensions of future habitats. Beyond the physical, psychologists and sociologists study group dynamics in simulated isolation habitats on Earth, like those in Antarctica or special closed environment facilities. They observe how small crews manage conflict, allocate resources, and maintain morale when cut off from the wider world for months. These studies provide invaluable data for designing the social architecture of a habitat, ensuring its community remains as resilient as its hull. Every solved problem, from a more efficient method of growing lettuce in hydroponic trays to a better model for predicting crew cohesion, is a piece of the larger puzzle clicking into place. We are not waiting for a single revolutionary breakthrough. We are systematically de-risking the future through countless incremental advances. Each prototype, each dataset, each lesson learned in orbit builds the confidence and the technical pedigree required for the monumental leap. The blueprints for rotating worlds are not static. They are living documents, constantly revised and refined by the quiet, persistent work of scientists and engineers who are already building our future in space, one experiment at a time. The silent work of prototypes and laboratories points toward a horizon far greater than our own survival. Our pursuit of rotating habitats does more than solve a problem of gravity. It answers a deeper, cosmic question about the nature of intelligent life itself. If humanity can conceive of building entire worlds from raw materials, of moving from a planetary cradle to a constructed home among the stars, then it is a logical step that other civilizations across the galaxy may have already walked this same path. This thought brings us face to face with one of the most haunting puzzles in science, the Fermi paradox. Named for the physicist Enrico Fermi, it asks a simple question with profound implications. Given the vast age and size of the universe with its billions of potentially habitable planets, why do we see no signs, no signals, no evidence of anyone else out there? One compelling answer, known as the zoo hypothesis or the sanctuary hypothesis, suggests we are looking in the wrong places. Our telescopes are trained on planets, scanning for the chemical signatures of life on rocky surfaces orbiting distant suns. But what if a truly advanced civilization does not live on planets at all? What if, after reaching a certain technological maturity, a species inevitably moves beyond the fragile biosphere of its home world? They might transition entirely to vast, self-sustaining habitats, constructed in the stable orbits of stars or drifting in the calm spaces between them. These cosmic arcs would be incredibly efficient, perfectly tuned to their inhabitants' needs, and nearly invisible to our current methods of detection. A Dyson swarm, a cloud of energy collecting habitats around a star, might register only as an unusual infrared signature, a dimming we cannot yet interpret. From this perspective, our own engineering efforts are not just a human endeavor. They represent humanity taking its first, tentative steps onto a potential universal pathway, a sequence of development that intelligent life may follow again and again across the cosmos. We are moving from a planetary species to a spacefaring one, and the logic of rotating habitats is a key milestone on that journey. This philosophical angle reframes every technical challenge we have discussed. When we calculate the tensile strength needed for a spinning ring or design a closed-loop ecosystem, we are not merely solving isolated problems. We are engaging in a fundamental activity of intelligence, learning to build our own context to carry our biosphere with us. It suggests that the ultimate end of a civilization's evolution might not be the conquest of other planets, but the graceful construction of its own tailored worlds. This thought redefines our place in the universe. We are not just inhabitants of Earth, we are potential builders of new Earths. The silence of the cosmos, then, may not be a sign of emptiness or inevitable collapse. It might be a sign of maturity, a quiet hum of civilizations living sustainably within their own engineered heavens, having left the unpredictable surfaces of planets behind. Our drive to build these habitats becomes a search for our own cosmic identity, a way to join a conversation that may have been going on for eons, hidden in plain sight among the stars. The blueprint for a rotating world is a testament to human audacity, a detailed plan for carving out a piece of home in the endless night. This engineering logic is not a single calculation, but a breathtaking symphony. Every note must be perfectly tuned, from the fundamental physics of spin and radius to the advanced material science of the hull, from the delicate biology of a closed ecosystem to the profound psychology of a community with no frontier. Each element is a direct, calculated response to a specific and unforgiving reality of space. We trade size for comfort, accepting the monumental challenge of construction to avoid the disorientation of a nauseating spin. We weave shielding into the very walls and soil, turning necessities into a fortress against invisible radiation. We design not just for the body, but for the spirit, understanding that a window to the stars is as vital as a water recycler. This is not science fiction or idle speculation. It is the rigorous, step-by-step extension of principles we already understand, a logical pathway from the International Space Station to a city among the stars. The equations are written, the material tests are underway, and the prototypes are already humming in orbit. We are solving the puzzle one piece at a time. As we stand on the brink of becoming a true multi-world species, these concepts offer us something far greater than a plan for survival. They provide a blueprint for flourishing, for building places where future generations can look up at an engineered sky and feel not confinement, but the boundless wonder of home. This future is a choice, one we make with every experiment conducted and every line of code written. If this vision of spinning cities under artificial suns excites you, consider subscribing to join us as we continue to explore the technologies that will shape tomorrow. We would love to hear your thoughts as well. What aspect of a space habitat fascinates or concerns you the most? Is it the social design of a closed community, the sheer mechanics of construction, or the simple question of what it would feel like to live inside a world you can see curve over your head? Share your perspective in the comments below.